Detecting tumors early can be the difference between life and death. But the tools we rely on today are not ideal.
The need is clear. 1 in 8 women develop breast cancer, and mammograms miss up to 20% of tumors, especially in dense tissue. Advanced imaging systems are expensive, bulky, and largely unavailable outside major hospitals. So current imaging fails in 4 key ways: cost, radiation exposure, accessibility, and lack of real-time monitoring.
What if there was an affordable, non-invasive way to detect tumors earlier?
What we want instead is a safe, repeatable screening tool that can be used frequently and anywhere. This is where we come in.
Introducing EIT Tumor Detection. A low-cost, non-invasive method for early tumor detection using electrical impedance tomography, EIT. How it works.
Electrical impedance tomography works by injecting a small alternating current into the body and measuring how it spreads. The key physics is that different tissues conduct electricity differently. Tumors typically have higher conductivity, higher water content, and altered cellular structure. So when current flows through tissue, a tumor disturbs the internal electric field. That disturbance shows up as a voltage change at the surface. We're not imaging the tumor directly, we're detecting how it perturbs the electric field. EIT has been studied before, but adoption has been limited. The main issues are weak signals at depth, low spatial resolution, and poorly optimized electrode design. Most prior work focuses on belt or ring arrays. Our approach is different. We focus on a handheld 4-electrode probe and explicitly study how electrode geometry, depth, frequency, and tumor placement affect detectability. This is a design-driven EIT study, not just demonstrating feasibility, but defining how to make it work. The probe uses a tetrapolar configuration. One diagonal electrode pair injects current, and the other pair measures voltage. Separating current injection from voltage sensing removes electrode contact resistance from the measurement. Before we show results, we want to address key assumptions in our model. Our tissue is simplified intentionally to isolate the effect of electrode geometry, following standard EIT sensitivity analysis. We also don't model contact impedance, but our tetrapolar setup minimizes its impact for this type of study. And while simulations can be optimistic, our signal levels fall within published ranges and exceed clinical detection thresholds. Overall, these results provide meaningful insight, and with further research, show strong potential for real-world application. We studied 2 configurations, a localized patch probe and a circumferential belt. Both operate on the same physics, but with very different field geometries. We built on the COMSOL electric sensor model and adapted it for biological tissue. Physics used: electric currents, frequency domain at 100 kHz. This captures both conductivity and permittivity through complex admittivity. Boundary conditions: 1 volt applied at one drive electrode, ground at the opposite diagonal electrode, all other surfaces electrically insulated. The sensing electrodes are passive, no boundary condition is imposed. Voltage is extracted in post-processing. Here's the full 3D geometry: tissue block, 4 surface electrodes, and a tumor inclusion at variable depth. The current density plot shows current concentration between the drive electrodes and a clear perturbation at the tumor boundary. The potential plot shows smooth equipotential lines, except where the tumor distorts them. That distortion is the signal we're measuring. Detection is quantified by the normalized change in differential voltage between the sensing electrodes. Without a tumor, the voltage difference is stable. With a tumor present, one electrode voltage increases while the other decreases. That opposing shift confirms asymmetric current redirection, exactly the physical signature expected from a conductive inclusion. We swept tumor depth from the surface to 15 centimeters. Signal change decreases with depth, as expected, about 17% at the surface, 10% at 5 centimeters, 5% at 10 centimeters, and nearly 4% at 15 centimeters. Crucially, every measurement exceeds the 1 to 2% EIT clinical detection threshold. This probe maintains sensitivity across the full clinically relevant breast tissue depth range. Changing electrode placement significantly alters the current distribution. When electrodes are positioned further apart, detectability improves. When current stays near the surface, deeper tumors become invisible, as shown on the graph. The 4 cm from edge configuration produced a peak signal of 26.64% at 15 cm depth, compared to 17.34% for the 2 cm configuration and 17.07% for the 1 cm configuration. A 53% improvement just from repositioning electrodes. Tumor size also strongly affects signal strength. At 5 cm depth, tumors below 2 cm fall near or below the detection threshold, while tumors 2 cm and larger are consistently detectable. This establishes a realistic detection limit and aligns with reported EIT experimental data. The central insight is this: detectability depends on whether the tumor intercepts the dominant current path. When the tumor lies in a high current region, detection is strong and reliable. That means electrode geometry, not tissue physics, is the dominant design lever. To explore deeper and more complex anatomy, we developed a second model, a circumferential belt with 8 electrodes. This geometry produces a more uniform cross-sectional current field and improves penetration through muscle and bone. Same physics, different field topology. This model includes layered tissue, fat, muscle, bone, and a tumor inclusion. The current is forced to wrap around the full cross-section, eliminating blind spots seen in localized probes. This is much closer to real limb anatomy. Detection is calculated using the normalized voltage deviation between healthy and tumor cases, accounting for layered tissue background effects. Even with bone and muscle present, signal deviations exceed 10%. Compared to the simple tissue model, signals are more distributed, but still strong. This shows the belt design trades localization for robustness in complex anatomy. E3 and E4 are high in the tissue-only case because they sit near the maximum voltage gradient created by the drive electrodes. In homogeneous tissue, the field is smooth and symmetric, so electrodes placed along the dominant current path naturally see larger baseline voltages. Peak signal deviations exceed 20% at optimal alignment. All electrodes register detectable changes, confirming there are no blind spots and that the system can track tumor position dynamically. There are honest limitations. Tissue is simplified. Electrode contact impedance is not modeled. This is a forward problem, not full image reconstruction. However, these simplifications are appropriate for a sensitivity optimization study, and signal magnitudes align with published EIT data. In practice, a clinician or patient applies gel, places the probe, and scans the region of interest. Measurements take under 1 second and can be repeated safely. Suspicious regions are flagged for follow-up, not diagnosed. Patch probe. Best for localized screening like breast tissue. Belt system. Better for
This
limbs and
project
deep
answers a
layered
foundational
anatomy.
question.
Each
Is there
design
enough
solves a
signal in a
different clinical
handheld
problem.
EIT probe to justify building it? The answer is yes. Across 2 geometries, multiple depths, and realistic tissue models, signal levels consistently exceeded clinical EIT detection thresholds. More importantly, we identified when detection fails, why it fails, and how geometry fixes it. The logical next steps are hardware validation, noise-aware modeling, and multi-electrode optimization, all now grounded in first principles physics instead of trial and error. This is research worth investing in.
This project answers a foundational question. Is there enough signal in a handheld EIT probe to justify building it? The answer is yes. So what if you had a device that offered reliable breast cancer detection anywhere? A groundbreaking handheld EIT device that allows nurses to identify breast tumors fast. It's user-friendly and portable. Breast cancer is the most common cancer in women worldwide. In low and middle-income countries, where the majority of the world's population lives, MRI machines simply do not exist. Mammography is unavailable. Women find tumors by touch when it is already too late. We are not proposing a replacement for MRI. We are proposing a first line of defense. A device that fits in a bag, that detects tumors early enough that treatment is still possible. Sounds promising? The physics works. The simulation proves it. The signal is there. What is missing is the investment to build it. This is your opportunity to invest in a life-changing mission. Invest in EIT tumor detection research.